All right, I'm going to explain exactly why the Hamiltonian operator in the Schrodinger equation is the energy operator and why it's called the Hamiltonian when Hamilton didn't work in quantum mechanics. He was dead long before the field was even devised. But here's why. So here we have canonical transformations. And what a canonical transformation is it's a way to map one set of an object's coordinates in phase space from one space to the next. So essentially what you do is you have an object that has position and momentum. And you can do these different types of canonical transformations, and you can move from one coordinate system to the next. And I'm just going to give you a very brief overview. I'm not going to get into the mathematics of this, but Hamilton discovered these canonical transformations, and he started doing mechanics in phase space. Phase space is when you have both position and momentum that you're looking at for an object's trajectory. So in other words, you don't just have its location as information, you also have its velocity, or if you just multiply it by its mass, then it's its momentum. That's a canonical set of coordinates. In three spatial dimensions, it's actually a six-dimensional space. Okay, so how does that relate to quantum mechanics? Here's how. Because when you act on a wave function, you produce a canonical transformation. That's right. The quantum object in question, the wave function that's associated with this quantum object, obeys canonical transformations. So when you act on the electron's wave function, you can change its coordinates in a way that's consistent with canonical transformations to an extent. It's a little bit different because in classical mechanics, we don't have probabilities for certain outcomes. Everything is definite. So there's still some modifications. But what's interesting is that there are symmetries in quantum systems, geometrical even, that are very deep and important to particle physics. And that's why you hear about group theory. This is also where group theory and studying geometrical relationships for systems and how they form different groups is so important in physics as well. It all comes about with this realization of these canonical transformations being relevant to the fields of modern physics. So next time when you're working with a Hamiltonian in the Schrodinger equation, you can think this realization that if we work with a system in phase space, it's very useful. And we can abstract this to fields as well. That's another reason why this is so useful. It works not just for objects, but also for fields.